Hello, everybody, and welcome to Know All for GCSE. So, in this first live for the half term, we'll be going over the first half of the AQA Level 2 Further Maths specification. So, this is specific to further maths in terms of topics, but I don't know how applicable it is for other exam boards. So, we're going to be using the whiteboard in this session. Um, ooh. And so you can see here on the screen now are literally the plan of everything we'll be doing. So you've got in today's live the first half of the topics. On the Thursday live, you've got the second half, and then you've got the two night before the actual exam lives as well, where we will be focusing on doing past papers. Okay. So if there's any issues with volume or anything, just let me know in the chat, and I'll hopefully be able to respond. Hello, everybody. It's nice to see you all here. So yeah, you can use this. That's how we're going to do it. And the way I'm going to go through it is go through examples for each of the topics, teaching you everything there is to know about it. Okay, so if anybody has any questions, do let me know. But yeah, let's get started. Hello, everybody. I'm going to share my screen. Now, obviously, some of the topics you don't need to know that much on. Some of them you need to know a lot more on. So it depends. Okay. And you can screenshot what's on the screen now because I'm going to just change to the next page. If the topics on the screen that I showed are applicable, so you're going to just have to check that out because I'm not too aware for the other spec. So let's start with the first topic, which, as I said, was domain and range. Oh. So what is domain and what is range? So domain are the values that you plug in, the input, i.e. the values of x. And therefore the range are the values that are outputted, the values that you obtain. So they are the outputs, i.e. the y value. For example, when you have an equation which is y is equal to mx plus c, you get a value for y. So your inputs, your domain is x, and your outputs, your range is y. Okay, now let's look at some examples in which you can be asked about this. So first example, and try these examples on your notes if you want. So you're given a function, often presented as f of x, is equal to 3x minus 5. And you're given a restriction on the domain. Now you're asked to write down the range for this function. So how would you go about doing this? So just to recap, we've given a domain, so a restriction for the domain. You can only plug in values of x that are equal to or greater than 5. So if you have the answers, you can put it in the chat already. So what you want to do is you want to draw a graph that might help you. So we've got 3x minus 5, so you've got a straight line graph. And when x is 0, the y-intercept is minus 5 there. And you've got a gradient of 3, so it's positive, so it's going to look like that. I can see people with the correct answer already. And now we've given that the domain restriction is that x must be greater than 5, so you find where 5 is, it's probably around here. And what you then want to do is you want to almost cut it off and then cut off the y value. You plug in the value for y when x is 5, so you've got 3, 5 minus 5, which is 10. And the graph helps you to visualize what the y value has to be. So since x has to be 5 or greater, y has to be, or f of x has to be equal to or greater than 10. So you can't just say 10, you've got to say greater than equal to. Well done, Chidima. Well done, everybody else getting it correct. Okay, now let's do a similar one where you have to, again, find the range. So you're given another function, g of x is equal to 7 minus 2x. And you're given that the domain is x is greater than equal to 2. Now, can you find the range of g of x? So again, you want to do a similar sort of thing. So what you want to do is, I can see people saying it already, you just draw the straight line graph. Now we've got a negative here, so we know that it's a downward sloping graph, and we know that the y-intercept is going to be 7, so it's going to look like that. And then plug in, so we know that x is 2, so x is 2 is probably somewhere here, and x has to be greater than equal to 2. So find the corresponding y value, which is 3. But since x has to be greater than equal to 2, y has to be less than or equal to 3. So that is your answer. Well done for those getting that correct. It is less than or equal to, and that's the importance of drawing the graph. As you guys, some of you I can see are making mistakes there. So the graph is downward sloping, so you need to be careful, because since x has to be greater than equal to, you notice that as x increases, y decreases. It's a decreasing function. Okay, good. Well done, Ishan, for getting it, and everyone else for trying. Okay, so that is domain and range. Now, another key thing you need to remember about domain and range is excluding values from the domain. So why do we exclude values from the domain? Well, you've got to think of graphs which have asymptotes, for example. For example, the reciprocal graph looks like that. So in the reciprocal graph, you notice that x never equals, or y never equals 0. So since y never equals 0, you're excluding the value of it being 0. So you're excluding values from the range and domain. Okay, and people are also talking about the tan graph. Well done, that's another thing that you can mention. So excluding values from the domain, this is essentially done to avoid normally dividing by 0 or square rooting negatives. So the reason why you can't have certain values is either because you're square rooting a negative value, or you are dividing by 0. And either way, you're going to get a maths error. Yes. Okay. I'm going to give you some more questions to practice with domain and range now. So example 3. Can you find the largest possible domain for exponential graph? Well done, Gayatri, that's also correct as well. So find the largest possible domain for the following function. So function A, f of x equals root x plus 1, and B, f of x equals 1 over x plus 5. So what are we going to do now? Find the largest possible domain, the largest possible values that you can plug in. So in this case, what can't x be? Well, as we said, we don't want to square root negatives. right? We don't want to square root any negatives. So when will the answer be negative? Well, when x is equal to 0, you have square root of 1, which is fine. When x is equal to minus 1, you have the square root of 0, which is fine. But when you have x is equal to minus 2, then you get square root of minus 1. So what our largest possible domain is that x has to be a value that is greater than or equal to minus 1. Okay, that's the largest possible domain. Now, don't get confused when it's saying largest possible domain, you're thinking that's the biggest possible value you can input. No, the largest possible domain is the largest possible number of values you can plug in for x, and that is when x is greater than or equal to minus 1. Okay, now our next answer, f of x is equal to 1 over x plus 5. So, what did we say we want to avoid? We want to avoid division by 0. So we notice that if x is equal to minus 5, you get 1 over 0, which is, you can't do that. So in this case, the largest possible domain is that x can be a member of any real numbers. Now I'm just using A-level notation here, just to speed things up, but it means x can be a member of any of the real numbers, but x cannot equal minus 5. Well done for those of you who are getting that in the chat. Okay, and that is all we're going to do for domain and range. We're now going to move on to piecewise functions. So I hope you're finding this helpful. Now, there's not too much to know about piecewise functions. Okay. And yeah, I know some of you are too familiar with that. That's why we're going through it. It's not like a major topic. It's quite a small topic. Okay, so as people are saying, what is a piecewise function? Yep, it's a graph with multiple functions. For example, so let's go through an example here. F of x is equal to, and then you have this interesting little bracket there, curly bracket. And you have f of x is equal to, let's say, x plus 2, 6, and 12 minus x. Okay, now you're thinking, how can it be all of these multiple functions? Well, what happens is you're given then domains. So when x is between 0 and 4, it fulfills the first function. Then when x is between 4 and let's say 6, it fulfills the second function. And then when x is between 6 and 10, it fulfills the third function. So how would you draw that? Yeah, it can also be called composite functions. So now, how would you then draw that? Well, you've got to have your graph, and we're taking values from 0 to 10, so you know your domain for x values. And key points that we want to note here, we've got 4, 6, and 10. Now you can see that between 0 and 4, it's an increasing function, and you've got to see what's the maximum value of y when you have this domain here. And you can see when x is 4, y is 4 plus 2, which is 6, so it goes up to there. So between 0 and 4, it looks like that. Then between 4 and 6, you're told that y is just 6, so it remains exactly the same. And then between 6 and 10, you've got that it's 12 minus x. So what is the smallest possible value of y? Because you can see that it's a decreasing function, the gradient is negative. Well, plugging in the value when x is 10, you get 12 minus 10, which is 2, so it goes all the way down to 2. Like that. And that is, if you asked to draw the piecewise function, that is exactly what you would do. Okay? So I hope that makes sense. And that's all there is for piecewise functions. That's all you talk about, the specified domains and ranges. They could be like, okay, what is going to be the range for one of the different parts of the function? And that's easy. You can draw a graph and write that out. Okay. So we've done domain and range, we've done piecewise functions. We're now going to go on to binomial expansion. Can you do a quadratic one? So a quadratic piecewise function. You can have a portion of the graph which is quadratic, but the rest will be normal. But so they don't want to confuse you too much. They could ask you though. Okay, so let's go on to binomial expansion. So I'm going to go through explaining where binomial expansion comes from, the Pascal's triangle. However, it's not like you have to memorize this for the exam. It's just explaining where it comes from. It's deriving it for you guys. Hello, everybody coming into the chat. Okay, so binomial expansion. You've got something called Pascal's triangle. So Pascal's triangle is where you have triangle and you've got your first value is 1, and then you've got the second two values is the next row is 1 1, and then it's always that the outer sides are 1, and then the numbers in between are effectively the sum of the two numbers above it. So this number is going to be 2 because that's 1 plus 1. Okay, and then you've got 1 on the outside again, and then this is 3 because you add 1 and 2. This is also going to be 3 then because you're adding 1 and 2. And then you keep going. So 1, 1. This is going to be 4 because you're adding 1 and 3. This is also going to be 4 as you're adding 1 and 3. And then this is going to be 6 as you're adding 3 and 3. So this is the Pascal's triangle. Now, with Pascal's triangle, a key thing here to note is that there's symmetry. As you keep going on and on and on, you notice that there's almost like a reflection going on with one side to the other. So with that reflection, that's an important property. And where do the values of Pascal's triangle come from? Well, it also links to something else. So the thing it links to is if you're expanding something, right? So in your normal GCSE, you would have done x plus y, where x and y are specific values, squared. And you may be even able to do it cubed. But say if this number was really, really big, like let's say 14, and you're not going to individually do that. That will be too time consuming. So using Pascal's triangle is a way of expanding this in a very fast manner compared to individually doing it. Okay. So how does it work? Well, you use Pascal's triangle to work on the coefficients. So if we had x plus y to the power of 0, this is just going to equal 1, as anything to the power of 0 is 1. If you had x plus y to the power of 1, then that's just going to be x to the power 1 plus y to the power 1. Pretty straightforward. Now, if you had x plus y to the power of 2, then what happens is your first step is you take your first value, which in this case is x, and then you say x to the power there, and you put x squared, and then you put x squared plus, and then you have certain coefficients. So in this case, the coefficient, because we're on, this is the first row, right? This is the second row, and the coefficients, notice, of x and y, in this case, you just have 1. In this case, you have 1, 1. So the coefficients here will be the next row of Pascal's triangle, which is 1, 2, 1. So notice we didn't write this down explicitly, but the coefficient here is 1. And then the next coefficient is going to be 2 to tick off that one. And then what will the actual values be? Well, what happens is the x value decreases a power. So the x goes from 2 to 1. And then the y value starts increasing, so the y value goes to 1. So you also have an invisible bit here which says y to the power 0. Okay, so you've got 1 x to the power 2 y to the power 0 plus 2 x to the power 1 y to the power 1. And then you have your next coefficient, because notice we've got another coefficient here, 1. And then your x still decreases, so instead it goes from 2, 1 to now x to the power 0. And then your y keeps increasing, it goes from 0, 1 to 2, so y to the power 2. And therefore your overall expansion is x squared plus 2xy plus y squared. Now let's try doing this with cube. Okay. I hope nobody is confused, and I hope you understand it. But if you are confused, do let me know. So now if you have x plus y cubed, right? So we need to look at the next level of Pascal's triangle. So we've looked at this one, we've looked at this one, we've looked at this one. It's now going to be this one where you've got 1, 3, 3, 1. So Pascal's triangle values 1, 3, 3, 1. So those are going to be the coefficients. Oh, it stopped sharing. Let me share the screen again. We'll do an example. Yeah, we will. Yeah, the screen's come off. Okay, thank you. Thank you for telling me, everybody. I don't know what's going on. It's not letting me share my screen anymore. One sec. Okay, better. Here, that's better. Okay, so if we do x plus y cubed, you're using, again, the numbers from the Pascal's triangle as your coefficients. So 1, 3, 3, 1. So you have 1, and then you've got x power, remember, and then your y to the power 0. Okay, and then your next coefficient, which is 3 in this case. So 3, x to the power, remember, the x value power is decreasing, so you go from 3, so your next one is 2, and then your y value increases from 0 to 1. And then we've got another coefficient, we've got 3 again, so plus 3. Your x thing, so it goes from 3, 2 to 1, and then your y value is going from 0, 1 to 2, that's increasing. And then you've got your final coefficient there, 1, and then you've got x to the power 0, y cubed, and that's your expansion. Okay, so those are that's how that would work. And then you're expected to be able to complete this expansion for, let's say, x plus y to the value 4 or 5, and using that knowledge that you have. So let's do an example some people were asking. I would recommend doing this alongside me. So I think this is what example 4, expand 2x plus 1 cubed. So what you want to do here is you're viewing this as your first value, this as your first value, and then this as your second value. So again, we've got 3. So we draw a Pascal's triangle. Find the row where we've got the most 3. So this is our row that we care about, and we now expand. So what you want to do is what might help is if you start by expanding just for x plus y cubed. So our first power 1, x cubed, y starts off as 0, and then you've got to the 2, not 2, sorry, then you've got to the 3, the next coefficient, x squared y to the 1. Because what we're doing is we're expanding it for these values first, and then we're going to replace the x and the y with 2x and 1. So then you have 3x to the 1 y squared plus 1x to the 0 y cubed. Okay, and now what you're going to do is you're going to replace, which is 2x, and you're going to replace the y with 1, just how we have in this expression here. So what you do is you then have x, 2x cubed, put it in brackets first before you expand, because you often miss this step and the powers go all wrong. So 2x cubed, and then y is to the power of 0, so it doesn't matter. And then you've got 3, 2x squared, 1, plus 3 to just the power 1, y squared, so 1 squared, plus 1 y cubed, which is just 1 cubed. And then you can expand this now. So that's just going to be 8x cubed squared is 4. 4 times 3 is 12, so 12x squared. 3 times 2 is 6, plus 6x, and then you've got plus 1. Okay, and that's the expansion. Well done, Logan, for getting that correct. Okay, so that is it for binomial expansion. That's pretty much all it is applying Pascal's triangle to expanding different things out. Now we are going to move on to the next topic, okay? So the next topic is factor theorem, and then we've got sequences and limits, and then tangents and normals to circles. We're trying to go as fast as possible so that maybe at the end we can do a bit more practice of harder questions, but that's what we think, so you know. So now I'm going to look at, you can use NCR as well. That's actually in the A-level specification, but if you understand using NCR, if you have that A-level calculator, you can do that as well. Okay, so we're now going to go on to factor theorem. Yes. NCR is a calculator function which helps you have Pascal's triangle every time. Oh, it's on the GCSE calculator too. Perfect. That's good. Okay. Factor theorem. So we're now on factor theorem. So the theorem effectively states that for a polynomial, let that polynomial be of x, if we plug in a value, let's say a, where the polynomial, the y value for that equals 0, then x minus that value is a factor of the polynomial. So that is factor theorem. Okay, and if you ever ask what actually is factor theorem, that's factor theorem. So an application of factor theorem is when you cubics and sketch cubics and say this is the non-calculator paper, so you can't really type it into your calculator because you can type cubics in if you have that specific calculator. In this case, then you're going to use factor theorem. So starting with an example for a quadratic, right? So if you wanted to factorize the polynomial x squared minus 7x plus 12, if you wanted to factorize that, it's kind of like the guess method. So you find a value for x for which it equals 0, and then you know one of the factors and you can work out the other factor. So for example, let's try when x is 1. So when x is 1, you've got 1 squared minus 7 plus 12. So 1 minus 7 is minus 6 plus 12. So that's way too small to get 6. So let's try another value. Let's try 4. You've got 4 squared, which is 16 minus 28 plus 12. And look, that gets you 0. Hence, we know that x minus 4 is a factor. That's an application of the factor theorem. So that's a factor. And then what you want to do, the main application, they won't ever ask you to use factor theorem for quadratics. They'll ask you to do it for cubics. So let's do an example here. Can you factorize I think this is factorize and sketch f of x is equal to x cubed plus 6x squared plus 11x 6. We weren't trying to make it equal 6, we were trying to make it equal 0. So we were plugging in different values. Is this suitable for OCR? I'm not too sure, you're going to have to check, but I think it should work. We're going to do this using the factor theorem. Let's say they asked us specifically to use the factor theorem. Then what we're going to do, so what we start off with is we try and plug in values for x to get 0, okay, because that's going to find one of the roots. Remember, the roots of any polynomial is where it intersects the x-axis. So let's plug in some values, and this is pretty much guesswork. So we need to guess the value. Let's say 1. So 1 cubed plus 6 times by 1 squared, which is just 6, plus 11 times 1, which is 11 plus 6. So you've got 1 plus 6 plus 11 plus 6, and that's definitely not equal to 0. So let's try another value. Let's try f is equal to minus 1. Sometimes it can be negative as well. You've got minus 1 cubed. Now, minus 1 cubed is minus 1. You've got minus 1 squared times 6, which is going to be plus 6. You've got minus 1 times again, and this is equal to 0. Hence, we can then say by factor theorem, you don't have to put this, but it just strengthens, it shows the examiner you know your knowledge. By factor theorem, we know therefore that x minus minus 1 is a factor, and therefore x plus 1 is a factor. So what you then want to do, now you have one of the factors, is you can then do polynomial division to find the other two factors, or to find the quadratic. Now, a lot of people get scared using polynomial division. I always use the table method, which worked for me, and it worked even during A level. So I would recommend you do that if you are confused with the long division method. So what we have here is we have this cubic, and we have our first factor. So if we divide this by that, we should get a quadratic, which we can solve. Wait, I'm confused. No, minus 1 is a factor. But remember, if the polynomial, if you sub in a value for x, example A, works, and you get 0, then remember, x minus a is a factor. And since we've got our polynomial, our a value is minus 1, then x minus minus 1 is going to be x plus 1. Okay? Hopefully that makes sense. Yeah? Okay, so continuing on now. So we're going to do our table method for division to try and get that. So what you do is you draw out your table, draw out 2 lines just like that, and then you write at the top the expression that we have already. So we've got x plus 1. Okay, and we are trying to achieve our cubic, and our cubic, as we said, is x cubed plus 6x squared plus 11x plus 6. So that's what we're trying to get. So we're effectively saying, what can we multiply this value by to get this value? So we start off by saying, okay, we've got x and we want x cubed. So what do you have to multiply to get x cubed? Well, x squared. Okay, and you then multiply each of the values by x squared. So x times by x squared is x cubed. And then 1 times by x squared is x squared. Okay, so now we have x cubed, which is fine, but we have x squared. We want 6x squared. So what do? We have to find a way of getting 5 more x squareds. So to get 5 more x squareds, what do we have to multiply this value by? X. Because what you then do is you do 5x times by x, which is just 5x squared. And therefore, we've got our expression so far. We've got x cubed and we've got 6x squared. Now we have 5x as well because we have to multiply these two values together. And we don't want 5x, we want 11x. So how do we get to 11x? What you then do is you then think, okay, we've already got 5, so how do we get to 11? 11 take away 5 is 6, so you then do 6. So you then have 6x, and then you've got plus 6. So you've got our 11x, and notice it always works nicely because you end up with u. So this is now our quadratic. So our factors are x plus 1 and x squared plus 5x plus 6. And then you can do your normal method to factorize this final quadratic, which should give you x plus 2 and x plus 3. And that is our factorized cubic. So that's the way I do it. It's up to you. It works better if this is a grid method, but there's also the long division method, etc. They won't ever ask you specifically to choose one method. It will be up to you. Yeah, it won't specifically ask you to do one method. Okay, now I'm also going to show you another question, which comes up, and it's just will show you how to answer it because you could get asked this. Which example is this? This must be example 7, yeah. So they could ask you, prove that x plus 3 is a factor of, and then in this case, you've got a to the power of 4. So 5x to the power of 4 is 45x squared minus 6x minus 18. So you just can be given a question like that. And just so you know how to answer it, I'm glad. Thank you, guys. I'm glad you're all here watching. I hope you find this helpful. So you've got that, and what you want to do is all you have to do is physically, because it's proof, it matters how you show you're working. So because it's proof, you have to go, okay, you're plugging into this polynomial. What value are you plugging in? Well, you can start off by saying via factor theorem, if x plus 3 is a factor, because we don't know if it is yet, we're trying to prove that. So if x plus 3 is a factor, thank you, L, I appreciate that. And thank you, Maxwell, as well. Via factor theorem, if x plus 3 is a factor, then f of minus 3 should equal 0, i.e. plugging in x as minus 3 should equal 0. So then what you want to do, you've got to have, this is not just one mark. So then what you want to say is via factor in blah, blah, blah. And then you want to actually find out what x plugging in minus 3 is. And you can't just put equals 0. You've got to show that you've subbed it in. So you've got to put f minus 3 power 4 plus or minus 45 minus 3 squared minus 6 minus 3, etc. blah, 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 to minus 18, and you work out it actually does give you 0, and you then say, hence, x plus 3 is a factor. Okay. Okay, and that is it for looking at factor theorem. So we're now going to look at tangents and normal to circles, and then we might do some practice, although we only have 10 minutes left of the live, so that will probably be it. Good timing. And then make sure you attend the second live, which will be going through the second half of the topics. Okay, so let's look at sequences and limits. So, really similar to GCSE, really. Let's start by going through an example. So, example 8. I'm going to give you here. So, what would be the nth term of this sequence? Okay. So that is our sequence. So how would you, well, now this is a type of question which either you've done and you know how to answer it, or you've not done it before. So what you've noticed that is there's two set sequences. There's a sequence for the numerators and then there's a sequence for the denominators. So you treat them separately. So what do we notice? Let's write them separately. You've got the numerators on one side, and then you've got the denominators on the other. And you've got two different sequences. They don't have the same way of working. So for this one, you've got 2, 12, 28, and 50. So how does that work? Well, what's the difference between this and this? You've got 10. What's the difference between this and this? You've got 16. And what's the difference between 28 and 50? 22. Now, if you work out the differences here, because those numbers are not in common, the difference is 6 each time. So you've got a quadratic there. And then for this one, what do we have? You've got 5 plus 2 is 7, 7 plus 2 is 9, and sorry, that shouldn't be 10. Sorry, that should be 11, shouldn't it? Yeah. And then, yep, that 9 plus 2 gives you 11 as well. So you've got two different types of sequences there. And this isn't explicitly, the topic of sequences isn't specifically on the spec, I think. It's just that I found that these questions, when they would trip me up. So here it should help you. It's more about limits that you get. So you've got two different types of sequence on bottom, and those will be your answers. So with the first one, we've got our quadratic, and I always have a way of solving it, but that's not really the common way of solving it. How I solve it is, I'll have to explain it to you guys. So the average quadratic sequence is always going to be ax squared plus bx squared. No, ax squared, sorry, plus bx plus c. So that's the average nth term quadratic formula. So if you were to look at the first three terms in terms of a, i.e. if you look at when x is equal to 1, 2, and 3, your terms are, you've got a plus b plus c is your first term. Your second term, you've got 2 squared, so you've got 4a, and then you've got plus 2b plus c. And then your third term, you've got 9a plus 3b plus c. Okay. So terms. So if you're finding out what's common between the first two, well, you notice that you've 3a plus b in common. And here, with these two terms, you've got 5a plus 2b okay. And then I think we ignored the c's for the minute. And then for that difference there, have I done this wrong? Two a, yeah. Oh, yeah, it's not 2a, sorry, the difference between them. So you're finding the difference between them. So that's going to be just 5a plus b as well. And then the final one is going to be 2a. So those are the differences between the different values. Yeah, you're right. It's 5a plus b. And then, so that is, I'm people, but that's what the quadratic terms would look like. And therefore, you can use that when you're actually looking at a quadratic. So this you can apply. So if we know that this value here, the second difference, is always in the form 2a, then we know that this second difference is always 2a. So 6, if that equals 2a, then a equals 3. Now next, the first difference between the first two terms always equals 3a plus b. Therefore, 10 equals 3a plus b. Now we've just found out what a is. So if a is 3, then you've got that 10 is equal to 9 plus b. You then know that b is equal to 1. Okay, and then you just want to work out c. So you know that the first term, 2, is equal to a plus b plus c. And we worked out what a is, which is 3. We worked out what b is, which is 1. So for c, we've got 2 is equal to 4 plus c. So c must be equal to minus 2. And then since we know a, b, and c, you write out the quadratic formula. So the quadratic formula is ax squared plus x plus c. So you then have 3x squared plus x minus 2. And that's how you solve it. Now, obviously, not every time I write out this entire formula, that was just to show you guys where it comes from. So I always remember that the second difference is 2a, the first difference is 3a plus b, and the first term is a plus b plus c, and that's how I memorize it. But people have different strategies. So overall, that should be your formula for the top. So your numerator, so our overall nth term will have the numerator as 3x squared, or 3n squared in this case, because we're doing the nth term, so 3n squared plus n minus 2. And then for the bottom, we've just got a simple arithmetic sequence. So what's happening here? Well, so you've got 2n, because our common difference in front of the n, so 2n. And then what's happening in each time? Well, for the first term, when n equals 1, you've just got 2, so you've got to add 3 to get to 5. So our nth term for the denominator is 2n plus 3, and that will be your answer. Okay, my second live is starting really, really soon. So let me just edit the time for that so we can finish this. Give me a second, everybody. Okay, I've just edited that, so let's keep going. So yeah, that's the nth term there. That is the answer to that question. So that's sequences, and just going over limits now. So what is limits? Limits, well, every sequence will eventually have a limit. So, and especially if it's exponential. So if it's exponential, it will tend towards a certain value. That's what a limit is. There will be multiple lives, yep. When n tends to infinity, yes, that's correct. Well done. So, let me give you an example and teach you through that. So let's look at this sequence here. You have got 1 over 2, 1 over 4, 1 over 8, and 1 over 16. So this is a sequence here. Now, what is the nth term? What's happening here? Well, you can see it's always 1 at the top, but then at the bottom, you've got 2n minus 1. Now, you should know this from your geometric formula, which is always a r n minus 1. So a is the first term, r is the common difference that's happening, the common multiplier, and then you've got n minus 1, which is the same thing. So that would be the nth term for this sequence. I've skipped a few steps so we can go through it. Now, as n gets bigger and bigger, especially for fractional, so any sequence where you have fractions, okay, you're going to have a limit. So as n, now you always use an arrow to show tens. So as n tends to infinity, what happens to this? What happens to this? So as n tends to infinity, then this value here, you get a number which is 1 over a bigger and bigger and bigger number. So overall, that becomes smaller and smaller and smaller and smaller. Therefore, 1 over 2 to the n minus 1 tends towards 0. It gets really, really, really close to nothing, but there's some sort of value there. Okay, and that is the overall idea. So let's do an example to help explain this to you. Find the limiting value. That's what they often phrase it as in the exam. (6n over 2n plus 1). So what is the limiting value there? Okay, so in this case, you've got to say, okay, as n tends to infinity, as n gets bigger and bigger and bigger and bigger, you want to find the millionth term and beyond. So as n is getting bigger, then what happens is 6n over 2n plus 1 tends towards, what would it tend towards? Well, as n gets bigger, how do you work this out? So the way you work out the limiting value, or at least the way that my school used to teach me, is just divide by n. Okay, so divide by n, because n, the impact of n gets smaller and smaller and smaller. So you can just ignore it. So you divide by n, the bottom and top, so you just have plus 1 over n. And as n gets bigger, 1 over n gets smaller and smaller, so you can ignore it. So that becomes 3. So 6n over 2n plus 1 tends to 3. Okay? You can effectively just ignore it. So we're going to do some more practice so that you're able to answer it, and then we will end the live, okay? Because I can see some people are confused. So let's just do some more examples. So let me say, can you find the limiting value of n plus 7 over n squared plus 8? So step 1 is always divide, get rid of the impact n, okay? So divide the top bottom by n squared in this case, because that's the largest power of n that we have. So what do we get? We get n divided by n squared is 1 over n. 7 divided by n squared is 7 over n squared. You've got n squared at the bottom, which is just 1. And then you've got 8 over n squared. And then when we have anything over the value that we've gotten, we know that as n tends to infinity, it gets bigger and bigger and bigger. So n squared tends to infinity, it gets bigger and bigger and bigger. So 7 over n squared and 8 over n squared can effectively be ignored. On top of that, 1 over n is also going to be ignored because that's getting smaller and smaller and smaller. So what do we have? We have 0 over 1 effectively. Now, if we have 0 over 1, then as n tends to infinity, our expression n plus 7 over n squared plus 8, that tends towards 0. Okay? So I hope that makes sense. Do we need to do another example? I think we need to do another example because some people are still confused. So So here's another example. 2n minus n squared over n squared plus 8. Do you need to? It depends on the number of marks of reasoning. Some people, I mean, you can't just put value. You need to put some sort of reasoning. So I would recommend writing it like that. I'm glad. Thank you for everybody here. Okay, for example. So we're dividing by the largest power of n. Again, we've got n squared. So that's the largest possible value. So that's step 1. Divide by the largest possible value. N squared. So let's divide everything by n squared. So 2n divided by n squared, well, that's just going to be 2n divided by n squared is going to be 2 over n. Now n squared divided by n squared is just going to be minus 1. N squared divided by n squared is going to just be 1. And then 8 divided by n squared is 8 over n squared. Now then we remove everything that's over n squared or n because that gets smaller and smaller and smaller. So cross that out and cross that out because its impact on the limit gets smaller. And then what you do is you now have minus 1 divided by 1. So as n tends to infinity, our expression 2n minus n squared over plus 8 approaches minus 1. Okay, so it's a limit. It never touches minus 1, but it gets closer and closer and closer to it. So I hope that makes sense. We went through a couple of examples. Maybe watch it again in slower speed if you need to understand that. And then I did say that we wanted to go over one final topic, which is looking at tangents and normals to circles. So that's, to be fair, that's exactly as GCSE, but you're more likely to be asked it because it's a harder element of GCSE. So we're just going to go over one final example looking at tangents and normals to circles, and then that's the first half of Further Maths done. Can you believe it? That's amazing. Yeah, I don't know if we have time to go over circles. You know what we'll do? We'll go over circles in the beginning of the next live. I think that will be better, most of the first half. So in the next one, we'll look at tangents, rearranging circles into general formula, differentiation, trig identities, and matrices. Okay, thank you guys, and I will see you in physics if you're going to be there. Physics is literally right now, and we'll be going over the content again using the whiteboard. Okay, see you guys there.